Welcome to Module 4 on Bridge Systems with Self-Propelled Modular Transporters. We're pleased to again introduce our speaker, Mike Culmo, Chief Bridge Engineer with CHA Consulting, Inc., and Principal Author for the 2018 AASHTO LRFD Guide Specifications for ABC. Mike?
Thank you, Mary Lou. In the world of ABC, we have the term that we commonly use, PBES, prefabricated bridge elements and systems. What we've been talking about up to this point are prefabricated bridge elements, or PBEs. Also, I like to refer to them as Lego bridges, where we build individual elements and connect them together in the field to create a bridge. Bridge systems, the second half of PBES, are much larger portions of bridges that are built adjacent to or nearby. We build an entire superstructure, in theory, build an entire bridge and pick it up in one piece and bring it in place and install it quickly. There are two major types of bridge systems in use in the United States that we have seen a lot, and they are SPMTs and lateral slide methods. We'll cover both of those methods and how you design a bridge for SPMT install and how you design a bridge for a lateral slide, and what are the responsibilities of the designer, what are the responsibilities of the contractor, and then we're going to talk about preliminary layout, and actually we're going to talk about dynamics as well. So a lot to cover in this module. So we'll dive right in. Again, SPMT systems are where we build the bridge in a nearby staging area, pick it up with these devices called self-propelled modular transporters, and we bring the bridge in one piece. And they've been around for quite a while, and I'll show some pictures in the next slide. But they are a very useful tool that we have in the ABC toolbox. But where are the preferred locations for SPMTs? Well, obviously, if you got a bridge over a river, you can't drive an SPMT in a river unless it's on a barge, which has been done. But preferred locations are bridges over busy highways where you want to limit the impact to the highway down below. Bridges over railroads where railroads are very busy and we want to limit the impact to the railroads. And then the most importantly, we need bridges with nearby staging areas, bridges that we actually can build, locations we actually build the bridge nearby and transport the bridge to this construction site easily. The guide spec, section 1 of the guide specification lays out responsibilities for the design of SPMT systems. And the designer has certain responsibilities and the contractor has certain responsibilities. The designer, first and foremost, is responsible for designing the bridge. They have to design the beams, the deck, the parapets, the substructures. The engineer has to design the entire bridge. We also want the designer to do a preliminary layout of the SPMTs because we also need the designer to specify the pick points and where it is safe to pick the bridge without damaging the bridge. And this has to include dynamic effects as well. So the engineer needs to do a preliminary SPMT layout. The guide spec gives guidance on how to do that. We want the designer also to verify that the travel path is reasonable. The photos on the right are showing two different SPMT moves. The one on the top is showing driving a bridge down a city street in Utah. The designer has to make sure the street's wide enough, that there aren't obstructions in the way, and that the machine can actually make its way down the road. You need to know the layout of the SPMTs in order to do this. So we need to bid a project, have a set of plans that is buildable. So the designer has to do at least some preliminary engineering with respect to the layout of SPMTs. We also want the designer to determine the allowable deformations in the bridge during the lift and the move, both vertical deflections and the twist in the structure, and then include that in the project specifications to tell the contractor how much twist is acceptable and what the anticipated deflections are to stay within. The header on the top of this slide is green, which means we are referring to a guideline developed under NCHRP Project 1298. This guideline is used to calculate dynamic forces on bridge systems using SPMTs. This is included in your handouts, so you can include that in your ABC library. And the key thing is the forces acting on the SPMT and the bridge and the SPMTs during the move is a dynamic event similar to an earthquake. We have a starting and stopping, we have accelerations and decelerations. We have a microphone in the background. We can mute our mics, please. There's also bouncing as the SPMTs traverse uneven terrain. We can get vertical accelerations. So we need to account for that in the design of the false work, but also the design of the bridge because the bridge will experience stresses as this occurs, primarily vertical bouncing. This was the guideline was developed under NCHRP Project 1298. I won't go into a lot of detail because there is an FIU monthly webinar dated July 20th, 2017 that goes into all the research that led to the provisions in this guideline. The guideline is very similar to the ABC guide spec and the AASHTO LRFD bridge design specifications in that it has guidelines and commentary as well. Briefly, what the research involved, we took SPMTs, added weight to the SPMTs and attached accelerometers and drove the SPMT through a series of maneuvers to simulate all the maneuvers that would typically be used for a bridge move. And we measured accelerations and decelerations in all three directions. The sensors were placed on different corners of the SPMT as well as on top of the weights. And we measured acceleration as longitudinal, transverse, and vertical. We looked at 3 different load cases. We applied 50 tons of weight, 25 tons of weight, and 15 tons of weight. And the reason for this is, logically, you know that, say, the deceleration and acceleration of a truck is dependent on the mass of the truck and the weight on the truck. Heavily loaded vehicle will decelerate slower and accelerate slower than a lightly loaded vehicle. We wanted to make sure we captured that, so we looked at 3 different load cases and interpolated that into create a design curve for this. And it made a significant difference in the dynamics. As far as the testing, the SPMT that I showed you before was run through a series of maneuvers. The first 3 were lifting the trailer up and down, the transporter up and down. The next 12 were horizontal start and stops at maximum speed. Maneuver number 8 was a turning maneuver. Maneuver 9 and 10 were traversing rough terrain at high speed. And maneuver 11 was a carousel or rotation maneuver. All these were done at the maximum speed the SPMT could accomplish. The idea was we're trying to calculate an upper bound for the accelerations and decelerations similar to a seismic event. What is the worst case scenario that could occur? And then we came up with load factors to account for the fact that it was an upper bound testing. This is the kind of results we got from the, in this case, this is the vertical accelerations with 15 tons of weight on the SPMT. And if you've studied any seismic design, you would look at this and say this looks similar to a curve that we typically design bridges for seismic, where we're plotting the period of the structure against the acceleration coefficient. We have these similar plots for horizontal and vertical accelerations and with different weights on the truck as well, on the SPMT as well. So we took that data and simplified it down to a simple idealized spectral curve, similar to what we do in seismic. So this is the curve for vertical response spectrum, and this is the curve for horizontal response spectrum. So for designing for horizontal dynamics, the design of the false work is similar to the design of a bridge pier for seismic. We have horizontal accelerations and decelerations, and essentially the top of the SPMT is the same as the ground in a bridge. The ground shaking occurs on a bridge, and it's applied to the structure above the ground. For an SPMT design, it's from the top deck of the SPMT up. It's just the same as an earthquake, and the research proved this out. We're using an ultimate strength design method. Again, we calculated the spectrum, the accelerations for the worst case upper limit that we expect. And for horizontal, it's similar to an emergency stop situation. For instance, if an SPMT was driving down the road and somebody noticed that the machine was, or the bridge was about to strike a power line, the operator might emergency stop the SPMT, which would create the highest forces, and we need to design for that. We decided to use an R-factor method similar to the AASHTO provisions. The key is we want acceptable damage but no collapse for this emergency stop situation. The AASHTO guide specifications for bridge temporary works includes design of false work for seismic, where they have recommended R factors for false work with limited ductility and medium ductility, and they're shown as 2.0 and 2.5, and that is carried through into the NCHRP guideline. As far as how to calculate these forces, we want to keep it simple, not make it too complicated. In theory, you could do a multi-mode spectral analysis of the system. Reality is, this is temporary work, so let's keep it easy. So we decided to use the uniform load method that's been in the AASHTO LRFD for years. That's based on the bridge acting as a single mass spring oscillator. We apply uniform load to the bridge, calculate a deflection, calculate a period, obtain a response coefficient, and then modify the loads based on that response coefficient. And we look at it both in the horizontal direction and the vertical direction. Very simple. One thing we also included in the guideline, though, is if you noticed before, the response spectra for both horizontal and vertical had a significant plateau at the lower end of the period. So for the preliminary design by the designer, we developed an equation that you can calculate the response of the bridge when you don't know the exact false work that's going to be used. You can conservatively design for that plateau. So we came up with a simple equation to calculate the horizontal dynamics and the vertical dynamics without even knowing the stiffness of the false work. And that is included in the guideline as well. I mentioned before, we want the designers to do a preliminary layout of the SPMTs to figure out, one, can they drive this down the road, and two, where can we pick up the bridge? So the guide specification includes these parameters that can be used for the preliminary layout: the size of these units, the width of the units, the length of the units, and the capacity. In the world of SPMTs, we refer to SPMTs as lines. The bottom detail on the right is a 6-line, which is a single wide trailer with 6 lines, 6 axles. Above that is a 12-line, and then when you go to double wide, it's referred to as a 12-line double wide. This is the terminology that we use in the ABC SPMT industry. So let's go through an example for a preliminary layout. We have a bridge superstructure. We have a bridge, total weight of the superstructure is 650 tons. So to calculate the number of axles required, or number of lines required, it's quite simply 650 divided by 30 tons is a recommended design, maximum design for each axle line. So we come up with 21.7. So we round up to the nearest 3. Typically, SPMTs are in units of 3. So we're recommending using 24 axle lines. So we're proposed to use 2 12-line SPMTs. They're 8 feet wide, and with the length of the SPMT, the axle spacings are approximately 56 feet long. The power pack goes on the end of the unit, typically 12 feet length. So the overall length of the SPMT is 67.5 feet. We need to make sure that, one, this fits under the bridge properly, and that, two, it can make the maneuvers required to get the bridge from the staging area to the construction site. So from here, we can locate the SPMTs in the desired location under the bridge and verify that the bridge can be picked. We also have to make sure that you can drive it down the road. Sometimes those two are not consistent with each other, that the ideal place to pick a bridge is at the end, but you might have slopes at the abutments that you can't get the SPMT that close to the end of the bridge. I warn you, do not move the SPMTs too far into the span. We have seen bridges with some significant cracks in parapets and decks by having cantilevers that are too large. A recommended maximum cantilever, from my experience, is about 15% of the span length, is where you should probably put the pick points, the maximum cantilever at the ends. So once this is all laid out, the designer should check the travel path to make sure this works along the travel path and at the bridge site. So as far as designing the bridge, the designer should follow the design of the AASHTO LRFD bridge specs for the design of the structure, but there's an additional check required to make sure that you can lift the bridge at the pick points that are specified. This should include vertical dynamic forces that I discussed a few minutes ago, where you use the simplified equation in the NCHRP 1298 guideline. So these are provisions in the guide specifications stating what I just said. The designer has to design the bridge. The contractor designs the false work and the SPMTs. That's the division of design responsibilities. So for checking the bridge, we're going to lift the bridge at these pick points. We need to make sure that we don't crack the deck excessively. You could use provisions similar to continuous girder design for this check. But the question is, how do I calculate the forces acting on the bridge when it's being driven down the road in SPMTs? So we recommend a service 1 check for cracking in the deck using a 1.0 load factor for dead loads. We recommend a factor of 0.4 for vertical dead loads, vertical dynamic loads, I should say. The reason the 0.4 is there is the testing was done at maximum travel speed of an SPMT of approximately 4 miles per hour. We recommend specifying a maximum travel speed of 2.5 miles per hour. And by reducing the travel speed, we found that vertical dynamics are a function of travel speed. So, and it's a function of the square of the travel speed. So by reducing the specified limit to 2.5 miles per hour, you divide 2.5 squared over 4 squared, and you get 0.4 roughly. And that's where that load factor came. If this becomes problematic, you can actually specify a slower travel speed and reduce this by a similar factor. Project specifications should include these maximum speeds. And we've checked with SPMT manufacturers, and these are not onerous specifications. Travel speed of 2.5 miles per hour is well within the normal operating range that they normally don't go even close to that fast. So it's not a very restrictive specification. If you want to check the bridge for strength under this lift, we give load factors for that as well. You use your standard dead load factors as specified in AASHTO LRFD, and the vertical dynamic load, you use a load factor of 1.0, again, because it's an upper bound, we're calculating an upper bound dynamic effect. For designing the false work and the SPMTs, we took into account the fact that most contractors still work in the world of allowable stress design. The AASHTO guide design specifications for temporary works includes load combinations for ASD design. So we came up with a load combination for ASD for SPMTs. Use 1.0 times dead load. Again, the 0.4 times the vertical dynamic load we mentioned before. But then for horizontal dynamics, see, the bridge superstructure does not see much in the way of horizontal dynamics because it's essentially a rigid body. But for the false work, does see significant horizontal dynamic forces, and we use a factor of 0.75. And that 0.75 is kind of a seat of the pants number that was developed by the project panel and the researchers. The guide spec for temporary works uses a load factor of 0.53 for seismic. So 1.0 is too conservative. 0.53 is too liberal. We picked the number in the middle of 0.75 as a recommended load factor to take an ultimate horizontal dynamic load and bring it into the world of allowable stress design. So that was a recommendation that's included in the NCHRP guidelines and in the guide specifications. So as far as analyzing the bridge, the guide spec section 1 recommends there's two ways of supporting the bridge in the staging area and for the analysis. The two methods are supporting the bridge on the ends, essentially supporting the bridge on the bearings during deck casting, or method B is supporting it at the pick points during deck casting. And the designer needs to specify one method or the other to the contractor because the designer has to check the bridge for these pick points to make sure it works. And I'll demonstrate what these look like. Method A is where we support the bridge on the ends, and this is a photograph of a bridge in Utah being built a number of years ago. And you'll see the impacts of this, and the impact really is when you go to lift the bridge, your standard deck casting, as far as stresses on the beams and stresses in the deck is in compression when you add composite dead loads, so everything is fine until you lift the bridge. When you lift the bridge, there are significant moment reversals occur at the pick points, and that can cause cracking in the bridge deck. So you'll see the deck moment diagram on the third line shows the deck in tension when it's being lifted and transported. That can be problematic. Once you set the bridge down, though, it reverts back to where it was in the staging area. So you have to ensure, the designer should ensure the bridge can be safely carried at the pick points without inducing excessive cracking in the bridge deck. Method B is a very innovative method that's been done in Utah. And this photo was taken from a Utah project where the contractor elected to support the bridge at the pick points. And they built this innovative framing where they could drive the SPMT underneath this frame and essentially lift this frame off of the piles and transport it. And what does this do for us as far as deck stresses go? And the answer is it does quite a bit. When you lift the bridge in the SPMT, you'll see the moment diagram. The deck sees essentially no tension when you lift it. The only tension of the deck would be due to dynamics. So it's a significant improvement. And then even better, when you set the bridge down on the final supports, if you look at the bottom line, the deck is actually put into compression once it's set. So it's a really innovative way of casting a deck for SPMTs to reduce cracking, and it does work. This bridge that's shown in the photo has virtually no cracking in it. It really works well, but keep in mind, this comes at a cost. That particular false work costs more than the false work you would have for a typical SPMT lift. So guide spec section 1 outlines not only designer responsibilities, but also contractor responsibilities. And the contractor is responsible for designing all the false work, for laying out the staging area. All the false work above the SPMTs is designed by the contractor. They need to include horizontal dynamic effects and vertical dynamic effects in their design. And they have to design for stability to make sure the system is stable during the move. We also want the contractor to do the final design of the SPMT layout and to do a final check of the travel path. We also would like the contractor to develop a monitoring system to ensure that the specified twists and deformations are not exceeded. As far as bridge analysis goes, early SPMT projects required the contractor to analyze the bridge. We prefer to have the designer analyze the bridge because the designer knows the bridge system much better than the contractor. But we do say that if the contractor decides to lift the bridge at a different pick point than what's shown on the plans, then the contractor needs to analyze the bridge for those new pick points. So this concludes Module 4 on self-propelled modular transporters and bridge systems using modular transporters. We covered designer contractor responsibilities. We covered the requirements for the design of the bridge. We covered the preliminary layout of the SPMT system. And then we also covered the dynamic effects of SPMT bridge moves. I'd love to answer any questions you might have right now.
Thank you, Mike.
We're quite ahead of schedules. Go away, fire away.
Paul Lyles will now moderate the Q&A session. Paul? Paul,
you're muted, I think.
Yeah, I'm here. Thank you, Mike, Mary Lou. We do have a few questions, not a whole lot, and we're a little bit of schedule, so we'll see how we do. The first question I have is, how do you design and select SPMTs? You showed that in there, how you went about doing it. Is there anything else you want to add to that? This question came in beforehand.
Yeah, that's fine. We give guidance in the guide specification based on several different manufacturers of SPMTs. There are other units out there, but they're all very similar. And the key thing is we know that multiple manufacturers and multiple heavy lift contractors can supply an SPMT to meet those requirements that are shown in the guide spec. So it's a good starting point. Contractors are fully allowed to come in with alternate machinery to do it. And we have seen some alternate machinery, but by and large, what's shown in the guide spec is pretty standard these days. Likewise, the research that was done under 1298 on dynamics was based on one of the SPMT manufacturers. We were told by the heavy lift contractors that all of the SPMTs in the market perform essentially the same. While it's not a perfect science to calculate dynamics of SPMTs, we're much further ahead of where we were, say, 10 years ago, when we were essentially leaning on the experience of the heavy lift contractors to design the false work for an assumed dynamic force. We have worked with numerous heavy lift contractors, and typically they were using numbers in the order of 5 to 10% for horizontal dynamic force to design the false work. There really was no vertical dynamic effects that were being used. So the research was very useful. And what we're finding out, the provisions in the guide spec and in the NCHRP guideline will give us numbers in the order of about 7% of the dead load of the bridge is your typical horizontal dynamic force. And that's within the range of what the heavy lift contractors can design for. So the dynamic guidelines give you reasonable answers that are much better than picking a number out of thin air. And they're based on the actual stiffness of the false work, which is important. Stiff false work will behave differently than flexible false work. And it gives reasonable numbers that can be built. So specialty materials could be used, but really what we include in the guide spec is the vast majority of SPMT bridge moves that have been done in the U.S.
Okay. Did you study any about the bridge SPMT interaction?
That question has been asked before, and really what it comes down to is, again, the hypothesis of the research was that the SPMT driving down the road, starting and stopping, is similar to an earthquake. In an earthquake, we have the ground motion is at the ground level. So we say, well, as acceleration is at the ground level, let's take those accelerations and apply them to the false work in the bridge. We accounted for the stiffness of the SPMT in the fact that we actually did research on an actual SPMT that was loaded. So the response spectrum curves that we developed actually take into account the stiffness of the SPMT and the stiffness of the tires and the suspension within the SPMT. So by using the equation guideline, we are actually accounting for the stiffness of the SPMT. Now we're looking at the interaction of the two. Well, that becomes a very complicated problem. That would we felt at the development of the guidelines that was applying a level of sophistication that was probably not warranted. So we felt, the project panel and the researchers felt that we had sufficiently covered the interaction of the structure with the SPMT, and that and the reality is also the SPMTs are very stiff structures. They're very rigid systems. You can imagine the capacity of these things is huge, and they are very rigid with many, many tires. And the reality is, there's not a lot of interaction going on between the two.
Okay. We got a couple of questions here on the foundations. And so the first one was, what foundation design parameters are needed for the temporary superstructure erection staging areas? And any borings? Is it recommended to get borings?
Yeah, great question. We do recommend that the designer take additional borings at the anticipated staging area. Contractor may choose a different staging area or may move the staging area around. So the specifications for the project should include that if they do that, they should take additional borings. So there have been projects that have been bid without borings in the staging area, and requiring the contractor to take their own borings. The problem with that is you're imparting significant risk on the contractor, not knowing what the conditions are in the staging area. So we strongly recommend that at least several borings be taken where these temporary abutments are going in, so the contractor can effectively bid the job cost effectively, knowing what they're up against. As far as designing those foundations, the contractor is responsible for designing the foundations because it is a temporary works situation, and we want the contractors to be to have the flexibility to design either a deep or shallow foundation, and both have been used. So we give the parameters, the geotechnical parameters. In some cases, we actually do a geotechnical report for the temporary abutments with a recommended pile load or recommended soil pressure. But at the very least, we recommend designers give borings to the contractor so they can design their temporary foundations. I think I answered the whole thing?
That's good. There's some more here. We'll go to another one, but it all involves geotechnical stuff for the SPMT. What is the geotechnical spec for the ground so the SPMT can run safely? That's when you're transporting it from where you've built it to the erecting site.
The key thing is these SPMT axles typically have 4 tires per axle. And if you take the 30 tons and you do the math and you realize that the loads are not significantly larger than a typical dump truck driving down the road. So as far as pavement goes, these machines are specifically designed not to damage pavement. That's why there's so many tires. And so that's one thing to know. There has been concern expressed by utility companies on damage to utilities. And again, these machines are designed to transport heavy loads down roads. They're typically used for transporting power plant equipment and also all types of heavy loads, and power plant equipment is very common. So the experience has been the pavement is not an issue. The loads are slightly higher than, say, an HL93 wheel load. However, where the dynamics are quite a bit lower because we're traveling at such slow speeds. So it should not be a problem. I've heard, I know of one project where there was concern about a water main, an old water main right where the bridge was being set. There was concern about settlement. The settlement would cause damage. But in settlement analysis, it's a long-term thing. Usually the short-term duration of an SPMT passing over a utility, settlement should not be an issue. Again, we're dealing with significant number of axles and spreading the load out significantly. If there is concern of utilities, we have seen projects where steel plating has been put down on the road to even further spread out the load from the SPMT to the pavement and the utilities underneath. In worst case scenarios, more significant crane mats and bridging can also be used. So my suggestion is work with the utility companies to find out what an allowable wheel load is over the utility, an allowable footprint pressure. Unfortunately, if you ask that question to most utilities, their answer will be HS20. And so it's something you have to work with the utility companies to make sure they are comfortable that the SPMT loads will not damage the utilities. So it's something the designer should work on during the design of the bridge to come up with any concerns with underground utilities that might be vulnerable.
Okay, and then that will also go, I guess, for like drainage pipes, corrugated metal pipes, culverts, or anything like that.
Yes,
You
exactly.
say it.
Same
Yeah.
thing. Again, we're dealing with wheel loads, 30 tons, so 60,000 pounds spread over, in most cases, 4 or 8 wheels. And the wheels are spaced, the way they're spaced out, that our wheel loads are in the order of 15 kips per wheel. So it's not, again, if you feel there's a concern with that, you can specify more axle lines and just specify the maximum axle load for the SPMT is maybe instead of 30 tons, we go to 25 tons or 20 tons. Keep in mind, though, you're going to get very big SPMTs, and that could cause other problems, especially with regard to cost, because now all of a sudden we have a lot more axle lines than maybe is necessary. So the designer should look at the travel path, and if there are any concerns with, like in the East Coast, we have brick sewers. If there's a concern with a brick sewer, you might require bridging to be put over the sewer, or steel plates to be put over the sewer to protect it. So there's things that we can do to manage that. The key is we want to let the contractor know this in the bid package so they know what they're getting into and what they have to price out.
Okay. Then there was a question that can you say something about the installation process, support, and stability requirements during the SPMT installation? That's when you actually get to the bridge site, I think.
Yeah, we'll be talking later module. The last module will be talking about specifications where we include things like this. But the contractor's responsibilities include stability of the system. And that's one of the nice things about the horizontal dynamic forces that we calculate. That will force the contractor to design falsework that has significant lateral resistance, which will make it significantly stable. When the SPMTs are laid out by the contractor, they go into very detailed calculations of stability, and they add quite a bit of bracing to make sure things are stable. The best way to describe an SPMT, it's a fluid system, a fluid suspension with hydraulic fluid that flows between zones, and they can configure the SPMTs to have different zones. So they typically go for 3 zones, like a tripod, to make sure that they have a stable system. The SPMTs are linked together to do this in some cases. And that's all under the contractor's responsibility to make sure the stability is maintained. So that is included in the, we'll cover that later in a later module.
Okay. There was a question that came here that it came in during the presentation. It says, I've seen some double continuous spans being installed with SPMTs. Do you have any guidelines for this specific case, cantilever span and distance between supports at the center?
Yeah, the guide spec does include a few provisions for this. You obviously need more SPMTs. We typically see two SPMT units per span. So if you had a 2-span bridge, you'd probably have 4 SPMTs supporting the bridge. The only major change to the design of the bridge is the designer needs to specify an allowable differential elevation for the SPMTs. Let me try to explain that. Essentially, say the center 2 SPMTs that are near the pier, if they were the differential elevation between the abutment SPMTs and the pier SPMTs, say varied an inch or so, what would that cause stresses for the bridge? So we want the designer to specify an allowable differential deck elevation of the SPMTs, which, because you have a continuous bridge system, that would result in stresses in the superstructure. So we have provisions in the guide spec to say that if you have a situation like that, you would specify not only allowable twist, you would actually specify an allowable differential grade from one SPMT to the next to ensure that we don't overstress the structure.
Okay, well, is the twist worse than in a simple span, or the tolerances worse for a continuous unit?
Not necessarily, no. The twist is really a function of the cross-section of the bridge. And we have found that these bridges can handle significant amounts of twist without cracking the deck. So the designer should do a 3D model, and typical twist tolerances are in the order of 1 or 2 inches. These bridges, especially an I-girder bridge, are very flexible with regard to twist. So I think you'd find when you do the calculations, I've heard anecdotal evidence of bridges that had twisted 6-7 inches and didn't crack. So we obviously we don't want to have 6 or 7% twist, but the designer can calculate what an allowable twist is. The key concern is stresses in the girders and potential cracking of the deck. But again, from my experience, these most stringer bridges can handle significant twist.
Okay, using the SPMT, you mentioned that sometimes they're done on barges, and you said rivers, and well, I guess certainly still water like ponds and lakes, and
yep.
And maybe even some with salt water. But you want to you comment on that at all? Does the designer look at anything like that, or is it totally the SPMT guy that does it?
That is a special scenario. It has been done. We've moved a 400-foot tight arch using SPMTs on barges. The dynamic guideline does not cover this. We have notes in the guideline saying that's a special case, and if you have to move a bridge on a barge and you want to calculate dynamic forces, we suggest the designer, contact barge companies to get information on that. That is quite a different animal. It can be done. It has been done. And where the bridge that I'm referring to is in Providence, Rhode Island. It was the Providence I-195 I-way arch, it was called. It was a 400-foot tight arch, twin barrel tight arch that was built on land, transferred to SPMTs, and then rolled from SPMTs onto 2 large barges, then shipped 12 miles to the site. A very successful project. But when it comes to dynamics in that case, you really should contact some heavy lift contractors to get their information, because that's quite specialty work.
Okay. Can you comment at all on the cost of using the SPMTs?
Oh boy, that question always gets asked. SPMTs can be pricey, but you have to look at other costs. What we typically recommend is, let me back up a little. The cost of SPMTs can range anywhere from, for a simple bridge, $250,000 to over $1 million, depending on the configuration, the travel path, all the project specifications. And that seems like a lot of money, and it is a lot of money. However, we try to tell designers and decision makers is to look at total project costs. And there was an FIU ABC webinar by Connecticut DOT where their decision process looks at other savings beyond the bid price in ABC projects. And one of the key savings you can make is by shortening the duration of the project. The overall project, you can reduce your construction management cost, and you can sometimes and often offset the cost of the SPMTs by, say, taking a 24-month project and reducing it down to a 12-month project. That's 12 months of construction management that you can save on the back end. You pay more for the bid, but you save money on construction management. That's a whole other subject that there's been webinars on, so I'll just leave it at that.
Okay. It's pretty well the end of the time for this module, so we're going to go ahead and move on to the next module.
Very good.
Okay, thank you, Paul. We're now at the end of the 4th 40-minute module. Thanks again to Mike for presenting the 4th module. We'll now continue with module 5.